So I'll talk about a different resource which is limited as well. That's the electromagnetic spectrum, which we as astronomers use and which is threatened by what we call radio frequency interference. By that we understand all electromagnetic emission, which makes our observations either very complicated or in some cases totally impossible. Let me start by saying that radio astronomy is a very diverse field. Not all radio astronomers, not all types of observations are vulnerable to the same types of RFI. It depends on whether we do imaging or beamformed observations, whether we need long integrations, short integrations. All of these details don't matter that much. The important thing is that all radio astronomers are affected by RFI and all observations are impacted. Let me just say that radio astronomy also covers very different frequencies. You see the radio window in this little diagram, and the examples that I will show today are taken from these three telescopes at the Nançay Radio Observatory. So I'll talk about Nénuphar, LOFAR, and NRT. So we see we already cover a big part of the radio spectrum, and things are, yeah, quite similar, even if details are different. So that's one example. That's interference at what we call the NRT. That's a telescope observing at a gigahertz range. That's an observation between 1150 and 1800 megahertz. And that's a monitoring observation. It's not a science observation. So for 24 hours, we looked at the sky and we tried to see what we see. So for those not familiar with this type of diagram, yeah, we don't see much astrophysical signal in this. It's really just to check the quality of the sky. The only astrophysical signal is this little black bar, right? That's hydrogen in the galaxy. All other structure that you see is RFI. It's just junk we have to get rid of. All of these more or less vertical bars, all of that is interference. You see that usually it's at a fixed frequency, and you see a zone here limited by the blue. That's what we call clean sky. That's a region where we can perform good quality observations. So we can also, instead of checking just one day, we can observe for many, many days and make statistics, see how much of the spectrum is lost by RFI. That's what we did with a different instrument, Nénuphar in this case. And you see it depends on the frequency and on the time of the day, right? So we have better conditions for this specific telescope at night, where we're in the blue, so the interference rate is low, and some frequencies are pretty bad. And you also see that it depends on where you observe. So if we observe at a high elevation, we are better. If we observe close to the horizon, let's say at an elevation below 20 degrees, then the fraction of bad data increases a lot. And that's, of course, because most of the RFI sources are on the ground or close to the ground. So I'll skip the natural sources, which exist, but which are relatively rare compared to what artificial sources we have to deal with. And for those, I differentiate two categories. So there's things which emit where they shouldn't, where people may not even be aware of the emission. And that's all industrial activities. That's power lines, train lines, it's cars. Cars have emission, which is not nice. Microwave ovens, there's very famous examples of problems with that. There's computers. People don't suspect computers that much, but if you think about it, they have a clock which ticks at which ticks at a gigahertz frequency, and that, by the laws of physics, means if you're not very, very careful, they will radiate at 1 gigahertz. And that's precisely where we observe. And then there's intentional emitters. That's telecommunications, mobile phones, aircraft, and all that stuff. Right. So, of course, radio astronomers had to deal with interference with other sources for a long time, since the beginning, but it is an increasing problem. It's increasing because telescopes get more and more sensitive. So even something which might have been judged not a problem 50 years ago now is really something which we detect easily. It's also because there's more emitters, right? So for cell phones, we are about to switch from the 4G generation to 5G, which uses a much larger bandwidth, which is stronger, which is much more complicated for us to deal with. There's more computers, there's more satellites. We'll come back to satellites in a minute. And the emitters now fill the band at a much denser rate. Before, many emitters only emitted in part of their, or in much narrower band, and now people are searching for big data rates, so they fill big chunks of the band, which kind of makes sense. The problem with that is that the regulations were made at some point and they are not really updated very frequently to take into account these developments. So this is a few solutions that astronomers use to protect their observatories from interference. First, we try to put the observatories in remote places, far away from cities, far away from airports when we can, stuff like that. We shield our equipment and we try to push for other people to shield their equipment as well, right? You can build a computer which does not radiate too much, but it has to be done. And then there's a few which I'll look at in more detail. So there's the protected frequencies. The ITU, it's a United Nations organization, has allocated a few spectral regions for where radio astronomy is a primary user and other people are not supposed to use them. Sometimes they do, but usually it works. But the part of the spectrum that is reserved for radio astronomy is really small. It's just about 1 to 2%. And there's a problem with the regulation. It does not include all radiation. So sometimes the radiation are just not submitted to these regulations. That's a bit a technical point, but it's really a problem for us. So we also use radio protected zones around our observatories. That's the example of Nançay. The observatory is shown by these brown lines. Apologies. And we have zones where people are not supposed to emit, to build emitters, which is good because it protects us, which sometimes leads to problems. Like in this case, there's a village close to the observatory and people don't have cell phone coverage, which nowadays is indeed a little bit problematic. So we are trying to find a solution, but it's not easy. And then there's signal processing. If the signal is sporadic enough, you can pick it up, you can isolate it, and you can remove it. But it doesn't mean you get rid of just the RFI. It also means you get rid of the data, right? You just blank a cell in frequency and time space, and this part of the signal is just gone. You throw it away. There's more modern techniques using, for example, machine learning, where we try to restore part of the data. So we not only throw data away, but we try to reconstruct the part which we lost. So that's quite interesting, but it doesn't cover everything. If your emission is variable in time, for example, then your algorithm cannot guess what it can reconstruct. So it can even be misleading and lead you to wrong scientific conclusions. So it has to be used with a lot of care. And also it doesn't work if the band is full. I already mentioned that modern emitters really fill the band a lot. That's an example at the low-fi frequencies between 100 and 200 megahertz. So we have the FM band, which we knew about, so we don't observe there. And there's two bands between 160 and 200 megahertz, where you can see it's full. Everything is saturated. There will never be any astronomical observations in this band. And the only way to deal with it that we found is to remove those frequencies by hardware, because it's so strong. If we remove it in software, it is too late. It already contaminates everything else. So we have added an extra hardware filter which suppresses signal in this range. So if we now look at these different solutions that I have mentioned and check how they can deal with different types of RFI, I've differentiate self RFI, that's RFI from instrument at the observatory itself, for example. There's ground-based RFI, that's emitters on the ground. There's RFI from the sky, where again, I differentiate two. There's the intentional emission. There's a satellite flying above, and it sends, for example, a GPS signal. How do we deal with that? And there's unintentional emission. And if you look at it, most RFI, we have found ways to deal with it. We can shield our equipment, we build remote observatories, we have protected frequencies and radio quiet zones. So that works for most, but how does it work for the unintentional emission from the sky? That's now what we'll have to look at in the end. And this is a very recent question. I mean, we've talked about Starlink before. There's thousands of satellites in orbit now. It's not only Starlink, it's other satellite fleets as well. And that's an experiment that colleagues did with the LOFAR observatory. They observed for 1 hour, and they saw 68 Starlink satellites crossing their beam. The crossings took about a second, and this is what it looks like in our data. So again, it's as a function of time and frequency. What happens? Well, the little red boxes show the time where we expected the satellite to pass based on their orbital elements. And you can see very broadband emission, which is extremely disruptive, including in the radio protected band. And that's non-intentional, so they may not even know this emission exists. Well, now they know because we told them. And it's coming back to what I said, computers are very problematic. Well, if you think about it, the satellites are computers in space, right? So it's the worst combination we can imagine. And I don't have time to speak about the simulation. The important point is just the one observation I showed is totally representative. If you observe at a random time, all sky cells have the same problem at 100%, which, yeah, brings me to my conclusions. For the unintentional sky emission, you can build a remote observatory, but it doesn't matter. They will fly over the observatory. You can have a radio quiet zone. It doesn't matter because they fly overhead and they don't even know they emit. You cannot filter the emission. That's the very frustrating case where one person's noise is another person's noise. And we are indeed quite worried about the future of radio astronomy. So the only ways to deal with it is to update the regulations, which currently don't cover these cases very well, and to communicate between astrophysics and the satellite operators. The satellites could be shielded. It's technically feasible. So really have to talk with these two communities, but we have to do it now. Otherwise it will be a bit too late. Thank you very much.